In this video, I'm going to talk about transfer function. So in the previous video, I talked about how to use the Laplace transform and inverse Laplace transform to find a solution to an ordinary differential equation that is used to represent a linear time invariant system. So the basic step is we try to first use the Laplace transform to write ordinary differential equation into its S-domain, and then find a solution in S domain, because typically we only have difference equations, so it becomes simple to compute a solution in the S domain. And then we use the inverse Laplace transform to find a solution in the time domain. Okay. Now, one of the questions you may want to ask is, when we have a complex system, so we could represent a system in a series of differential equations. They are sort of connected in a certain way. So I will show you an example of what I mean by that. Let's consider example that let's say we drive a car, for example, and our goal is to drive the car from the car, let's say starting at a static at a certain location at certain velocity. I want to speed up to make sure that the car will move forward at a certain velocity. Okay, so typically the input we give is a force we apply to the pedal. So if you can see, that's the input, so input will be the force we apply to the pedal. Well, this does not directly control our velocity. The pedal, when we give input, the pedal will determine how much gas will be provided to the engine. So the amount of gas will be given to the engine. The engine will create a horsepower. The horsepower then drives the motor to create a force. The force then drives the car to speed up or slow down. Okay, so then they will determine the velocity. As you can see from here, the input output is not directly represented by some differential equation or directly. Instead, there are multiple processes, and each process can sort of be represented by from input to output represented by a differential equation. For example, assuming here all the steps are represented by linear time. So here we have a model, assuming that it's from the input, let's say the force applied to the pedal, to the number of gas, that's a linearized model. So we can represent this as ordinary differential equation 1. Okay, which means you can sort of consider here we have a linear system. Over here we have an input output, and we have the ordinary differential equation to represent the linear system, the control system basically. Similarly, we can also consider the amount of gas we apply to the engine and the created horsepower by sort of an ordinary differential equation. Okay, and so on and so forth. We can by considering the horsepower generated by the engine as the input to the motor, and the output as the force applied to the car. So that one we can also represent by ordinary differential equation. So lastly, the force we apply to the car and the output, which means the velocity of the car, can also be represented by another ordinary differential equation. So the general relationship between the input and output can be complex because you have a multiple process in between. So in other words, it's kind of difficult to figure out what is a big ordinary differential equation that can represent the relation between the input output. Okay, so now the question is, how do we describe the relation between the input output if the relation is quite complex? Okay, so there are basically two options. The first option is, well, I want to derive an ordinary differential from input output based on ODE 1, 2, 3, 4. For example, I probably have a state variable here. I got to write a differential equation, so output will be the amount of gas. Then this one we put a differential equation here again, so we have differential equation, so on and so forth. So let's, for example, you have ODE 1. You sort of some state x1 dot that's the input, and my output is the amount of gas. Let's say it's x2. Okay, some sort of relationship, maybe like 2x2 plus some 3, for example, whatever it means. And my ODE2 could be x2 dot, which is the horsepower is, let's say, x3. That's the horsepower plus 7, whatever. You can do this one. So you can write all the stuff together. Now what you do is write a differential equation. You want to derive a differential equation that can directly related input x1. That's my input x1. Output, let's say output is y of t. I can find the relation between x1 and x2. I want to cancel out all the intermediate variables. I only have a relation between x1 and my yt. Then that will tell us the ODE. That's the ODE I mean over here. Apparently, this approach can be complex, especially if we have multiple ODEs, and to cancel out this intermediate variable. For example, here, state this is the x2, x3, and x4. So this is the x1, for example. This is y. To cancel out intermediate variables, it can be tricky or can be difficult. Okay, so that option. The option 1 typically can be difficult. Okay, the option 2 is, why don't we describe each ODE 1, ODE 2, ODE 3, and ODE 4 in S domain? And hopefully the aggregation of these 4 in the S domain can be simple. And we have to find out the relation between input and output in the S domain. Then we do the inverse Laplace transform to find the relationship in the S domain. So that's the key concept we already mentioned over here. Okay, so key concept here is we want to describe each ODE 1, ODE 2, ODE 3, ODE 4 in the S domain. So the goal is hopefully once in the S domain I can figure out what is the input. This is in the S domain. To output is also in the S domain. So hopefully I can find a relation between the input and output in the S domain, not in the T domain, because in the T domain it's difficult. Then hopefully I can aggregate this input output relationship in the S domain directly, not in the T domain, because in the T domain it's difficult. Okay, as I mentioned over here, in the time domain you'll find the solution is simple, right? So hopefully that one, the input and output relationship in S domain can also be simple. Okay, and also hopefully the aggregation of the 4 to figure out the input from here to the output will be simple as well. So that's the option 2. Okay, so the key idea in option 2 is to use a new concept called transfer function. So that's the key focus of this lecture. Okay, before talking about how we do this problem, I want to talk about what is a transfer function. Okay, so the transfer function is exactly what I mentioned here. The transfer function is of a linear system or linear control system is defined as a ratio of the Laplace transform of the output variable to the Laplace transform of the input variable. So here there's a caveat. So with all initial conditions assumed to be 0. Okay, we don't assume that the initial conditions are non-zero. So we let all initial conditions to be 0. Okay, so that's called transfer function. Okay, so now let's talk about what is the transfer function. I'll tell you how we compute a transfer function. Okay, so first I'll give you a very simple example. Let's say if I give you a flat surface, is horizontal surface. So assuming there's no friction between this object, this is called object with a mass m. There's no friction, so here no friction. So the input is a force applied to this object. It's called u of t. The output is called velocity, which is the v of t. Okay. So I want to find the transfer function, which means I want to try and find the transfer function between the input and output. In other words, because my input is u of t, or output is v of t, according to the definition says the transfer function is a ratio of the Laplace transform of the output variable. So basically, I want to first find out what is the Laplace transform of my output variable. Output variable is v of t, okay? And to the Laplace transform input variable. The input variable, Laplace transform input variable will be L u of t. So L v divided by L u of t, that's the transfer function. This is a transfer function. Okay? So typically you can use a you can use TF, okay, to represent transfer, or you can use a G sub S to represent transfer function. There are two ways you can denote the transfer function in a mathematical way. So let's say I'm just using TF to represent transfer function between the input output and input in the S domain. So which means it's L of Vt divided by L of Ut. Okay. So the key idea is I want to compute this. Of course, I don't know what that means. I'll have to figure out what is that. Okay. So what we do is, well, remember we have to go back to the time domain, okay? Because I want to transform the operator variable in the time domain. I want to find so the relationship is defined in the time domain. So this one typically to compute this. So you have to find a relation between VT and UT, sort of UT, right? Some relationship, right? The differential equation. So this is driven by. So for example, Newton's law. For example, here, okay. So in order to figure out what's the Laplace transform, let's find out the relationship between Vt and Ut in the time domain, in the t domain, not in S domain, because we don't know how to do that. We have to find the t domain, okay? So according to Newton's law, I know, so this is my force applied to the object, assuming there's no friction, so which is given by m time acceleration, okay? Is m is the mass, a is the acceleration. Now a is the derivative of the velocity, so the operative velocity, so m times v dot, okay? Now we apply Laplace transform on both sides to see what's going to happen. So if I apply this guy, this is exactly what we want to have, okay? For the right hand side is L Laplace transform of m times v dot t, okay? Now this one we use, we can move this m, because m is constant, we can move m outside. Now this L of v dot t, we use the property of Laplace transform, which is m times s L v sub t minus v0. So this is the initial condition. Okay, remember this is the initial condition. Remember for the Laplace transform, we set all initial conditions to be 0, we assume to be 0. So which means, hey, I can set this guy to be 0, so it's gone. Okay. Now I can sort of simplify this as what? As this. If I do a simple notation as Lv sub t is v of s, Lu sub t is u sub s, so the notation wise, which means this is v sub s, this is u sub s. Okay, so now this guy means Lvt divided by Lut, because this guy is already 0, so this is Lut, this is Lvt, which means I have Lut is ms times Lvt. So Lvt, because I want to figure out what is Lvt divided by Lut, so I can move this one to the right hand side, so Lvt divided by Lut, and move this to the left hand side. Of course, that swaps the order. So Lvt divided by Lut is 1 over m times s. So that's my transfer function. So this is my final solution. Okay. All right. So now I'm going to find out the second example. Okay, it's a little bit complicated. Let's say this is a circuit which has the resistor and a capacitor. So the resistor R, capacitor is C, the constant R and C, okay? So this is the structure. So I have a resistor over here, this is a capacitor. So this input is V1T and the output is V2T, okay? So this is a voltage. This is a voltage. Okay, this is also the voltage. I want to find a relation between the voltage here and the voltage over here, okay? So in other words, I want to find a transfer function of LV2T, LV2T divided by LV1. This is the transfer function basically, okay, if I consider this input output. Okay, so the challenge, you may want to say, how do I find a relation between V1 and V2T, okay? So the challenge here is the relation between V12 and V2 is not directly seen over here. So it's kind of, I cannot find a differential equation directly described as a relation between V1T and V2T. So the goal is find the ODE, because I don't know what that means over here. So their conditions can be sort of seen via introducing an actual variable called current. The current goes through the resistor and the capacitor. Let's say, assume that is current of IT. So we sort of can first write a relation between this V1, and I want to see what is, if I, by introducing this current, I want to first figure out what is my relation between, between my current IT and my V2T. Okay, so this is fairly easy. If I already know the current IT over here, this current goes through here. So my velocity V2T, according to the capacitor, the V2T is just be given by this. V2T is just given by C integration of 0 to t I tau d tau. It's the integration of my current times this constant C, this gives us the voltage, the output voltage V2. So the input here, if I assume this input is IT, output is V2T, now I can sort of figure a relation between the transfer function between the input IT and the output V2T. Okay, if I do the change, if I do the LV2T, I apply Laplace transform on both sides. Okay, so left hand side apply this L here, get the LV2T equal to L of the right hand side, the C integral 0 T I tau d tau. Assuming here, this is definition, assuming that V1S is given by LV1T, this is Laplace transform, and V2S is Laplace transform of V2T, and capital LS is Laplace transform of LIT. So I get V2S. This is the user definition I give over here. So V2S is this is user property of the Laplace transform. Is C. You can put the constant outside. The integration, the Laplace transform integration 0 to T I tau d tau. This is just 1 over S times IS. Okay. Do you remember ISS here is the Laplace transform of IT, okay? By doing this, I have V2S divided by IS is C over S, because I can move this IS to the left hand side is V2S divided by IS, and this is C over S, okay? This is the relation between IT and V2T, okay? How about IT and V1T, okay? Assuming my V1 is input and V2 IT is output. So according to the circuit, so the velocity of V1T, okay, because they are parallel, so the velocity of V1T is not velocity, the voltage of V1T is given by the voltage for this resistor and the voltage for the capacitor. So which means V1T is given by R time IT. That's the voltage for the resistor R. And the voltage for the capacitor is again given by C integration 0 to T I tau d tau. Okay. Assuming here my input is V1T, output is IT. So again, apply Laplace transform on both sides of this equation. So L V1T, which is L on the right hand side, I use the linear property so I can separate them. So L I times IT, R times IT plus L times C of Laplace transform of C 0 to T I tau d tau. So separate them. Now this based on the definition is V1S. I use a simple notation. Because this resistor, the capacitor, the constant is a constant, so I can move it outside. So this Laplace transform of IT is IS. So C can be moved outside because C is a constant. The integration of the Laplace transform integration, again, over as I mentioned over here, is C 1 over S times IS. Okay? So because I consider input is V1T and output is IT, so I sort of want to get at what is the IS over V1S, okay? Which is if I put them together, so if I put this together, okay, let's see, put this, the right hand side can be written as R plus C over S times IS, the right hand side. So if I move this one to the right, so move this guy to this side, and move the left side, I have S divided by V1S is 1 over R plus C over S. So I do a little bit of simplification is S. If I time both sides by S, numerator denominator by S, so the numerator will be S, denominator will be R times S plus C. So that's my transfer function from V1T to IT. Also I have a transfer from IT to V2T. So here's the next, so now I still haven't solved the problem of the transfer function from V1T to V2T. Okay, now I'm trying to figure out how to combine both to find the transfer function. So if I let the input to be V1T and output to be V2T, that's what I want to find out. Okay, so it will be L V2T divided by L V1T. Okay, which will be according to the definition over here, so it will be V2S divided by V1S. So nice thing about the S domain here is, well, I can divide it into two parts. I can do is equal to V2S time divided by IS times IS divided by V2S, because essentially these two will cancel out. Okay, the reason I can introduce this actual one is because I already figured out these two individual components. This is I already figured out over here. It's given by here. So this is transfer function between IT to V2t. This is a transfer function between V1t to IT. So we already figured it out previously. So it's C over S divided by S times S divided by S plus C. So apparently this 2S will cancel out. So it will be C divided by S plus C. So this will be the transfer function. Okay. So here's another view that we can look at the transfer the problem that I mentioned over here. So generally, if I look at the very general problem I mentioned over here, I have an ODE 1, ODE 2, ODE 3, ODE 4. What's going to happen if I want to find a transfer function? Okay. So suppose I have ODE 1, ODE 2, ODE 3, ODE 4, okay, right over here. Okay, if I want to find the input, let's assume the input is UT and output is YT. If I want to find the Laplace transform between the input and output, according to the transfer function between input and output, so according to the definition of the transfer function, so it will be just LUT, right? This is the LYT. So that's the definition of transfer function, okay? So it will be LYT divided by LUT. So this one can be divided as, assuming I have intermediate, this is output here, x1t, this is x2t, this is x3t over here, okay? This is x1, this is x2, this is x3, this is output here, here, and here. So I can write this one as L of yt divided by L x3t. This is right over here. Okay, this is assuming x3t is the input and the output is yt. Time L x3t divided by L x2t. So here I assume I have input x2t, output x3t. Okay. Time again L x2t divided by L x1t. Okay. Assuming here my input is x1t, my output is x2t. And time the last one is L x1t divided by ut. So which means I consider the input is the ut and output is x1t. Okay. So this one can be written as a product of 4. The reason that this is true is because I can cancel out this one cancel out, this one cancel out, this one cancel out, this cancel out. You could basically cancel out all the intermediate steps directly. Okay, this is essentially what's going to happen for the, if you want to use the option 1 to do it, you still want to cancel out all the intermediate variables. Okay, the nice thing for the transfer function, as you can see from here, the intermediate variables by doing the Laplace it directly cancel out. So there's no actual work. Okay, we just need to figure out the individual transfer functions for each process, and we do the multiply. That's it. So it makes it very easy to compute to find a relation between input and output in the S domain. Okay. All right. So basically, we sort of need to figure out a transfer function for the first one, for this guy, for this guy, this guy, this guy individually. Okay. So you can sort of consider this as an individual block. It's called a block 1. This is block transfer function 4, transfer function 3, transfer function 2, transfer function 1. So you can consider this as each block. Okay. So this is called a block, right? Because you can see block 1, the transfer for block 1, transfer for block 2, transfer for block 3, transfer for block 4. So as long as you can do individually, you just need to do the product, the 4. You get the transfer function from input to output. So this sort of idea is called a block diagram, which means I can represent the system into different blocks. I only have to figure out each block individually, and then by looking at the relationship, I just to aggregate this block together, I can find a transfer function. Okay, so this one I can decouple this. The nice thing for the block diagram is I can decouple a complex control system into simple ones that are connected. So this simple ones is called a block. So because for simple ones a block is the transfer function is really easy to find out. So all the transfer functions will be combined according to the connection. I can combine those transfer function aggregate to find the overall transfer function. So that's a key concept of the nice thing by using the transfer function or transfer function, which means I want look at the relationship between input and output using this form: LYT divided by LUT. I look at the relation between input and output in the S domain, not in the time domain. Okay, so next time I will talk about what is the block diagram and talk about some key properties.